Dear colleague, my name is Wolfgang Bauer. I'm a professor at Michigan State University, and I would like to talk to you about creating virtual lab experiences under the constraint of physical distancing. So this is pretty much standard higher education plans for the fall of 2020. We need to reduce classroom fillings, so fill classrooms only by 15 to 20%. Need to move large lectures online, wear face mask all the time, stretch out instructions to the maximum extent possible, maybe from 7 a.m. to 10 p.m. every day but Sunday. And that still leaves students with pre-existing health conditions that have to be given a complete online option. And so then the question is what to do about hands-on labs. What makes a physics lab experience authentic? And I made this laundry list of tasks that need to be completed. Assemble the apparatus first, run the measurement, record the raw data, analyze those data possibly inside spreadsheets, form a hypothesis, draw some conclusions, estimate the uncertainties that your measurements entail, and write a lab report. So how can we do this online in a virtual environment? So in the first semester, we all teach mechanics, and we developed this video digitizer tools, which has this handy remote control that you see here. It's written in HTML5, and so it's usable on computers, on touch devices, on smartphones. We load pre-recorded video clips that connect physics concepts with everyday experiences. And I list a few examples here, like a billiard ball collision or a cup sliding across the surface or a basketball free throw. This is the complete list of the first semester experiments. And here, for example, is a billiard ball collision. And you see what the digitizer can do in marking the position of both balls at any time in the collision sequence. It generates some data in terms of frame number and pixel coordinates in X and Y direction, and some information which color you have used. You can take this data and copy it into a spreadsheet for further analysis and graphing. So let's look at one example. Here's a free fall simulation with an actual video recording like this, an apple dropping down into a bowl. So the digitizer lab looks something like this, and you can step forward frame by frame. Frame counter is here, and until you let go, which is about here, you can forward. And then you want to mark the position of the apple, and you can just do this by clicking on the screen like I've done here, or using your keyboard for accessibility features. Once you click, you see the data get recorded here. You can advance to the next frame, click again, next frame, click again, and so on. Once you've collected enough data, you copy them out and you paste them into a spreadsheet. And here's just a sample of what you can do with this spreadsheet. So these are actual data from the digitizer. The raw pixel coordinates are here, and then the converted physical coordinates are here. And in this case, the task was to fit the parabola to it to extract the value of the gravitational acceleration. And here, for example, I use 10 meters per second. I can also use, let's say, 9.5, and you can see this fit is not quite as good. In the second semester, you cannot use, in general, the same strategy of recording motions on video, because in optics and in electricity and magnetism, things just don't move the way they do in mechanics. But for circuits and optical benches, some digital replication of the physical measurement apparatus assembly is possible. For example, in this app that uses polarizers that are put into the path of a laser beam. And you can record the different angles in this case and the resulting intensities on the screen. So this is the complete list of experiments in optics and electricity and magnetism. Here's an example of resistors and batteries, and I'm just going to go to this lab. You can drag your different resistors anywhere into this circuit in the predefined positions. You can also drag the batteries and change their orientation. And then closing the switch, you measure the current. And you can see that the light bulbs shine with different brightness depending on where they are in the circuit and what current flows through them. You can also individualize the lab experience by integrating them into the McGraw-Hill Connect package, and then you can generate different numbers for different students, which of course then makes the lab experience harder to plagiarize. Here's another example, the famous double slit experiment, where you can manipulate real interference patterns, including the single slit refraction. So the lab may look something like this. You switch on the laser, you get this interference pattern on the screen. You can measure the distances between the maxima, and you can change the slit separation and the width of individual slits. So my personal bias for the scorecard for what you can do with these online labs is assemble the apparatus. Well, okay, you can put the batteries in, you can put the resistors in, they snap into place. This kind of assembly is possible. We have a Wheatstone bridge where not every resistor actually leads to a solvable Wheatstone bridge setup, and so you can to some degree replicate the frustration for using the wrong equipment. You can run the measurement just like you have done it in the lab. I put a partial question mark there because the possibility, for example, to electrocute yourself is not given, so it's to some degree safer. We can record the raw data just in a similar way as we do in an actual lab setup, and from here on out all the other steps are usually done in the computer anyway, and we can do them exactly the same way as we would do in real life labs. As a final note, I just want to stress that we just provide the tools for the students to investigate physical scenarios, and adopting faculty have the freedom to decide what questions to ask or use ours, and how to evaluate or use our scoring rubrics. Here's more information. There's my email, my webpage, the webpage for our textbook. It's not necessary to adopt our textbook for this, but of course I would like you to. Thank you for your attention.